Welcome everyone. It's great to see such a good turnout today. I think you all know by now there is a lot going on at the center today, and this is one of a few real keynote events that I hope you'll all be able to take advantage of. We've got students all over the center. We've got a poster session later today, free lunch, and Diversity and Inclusion Day. So let me start by sharing with you the lament of a senior manager, that there are many things that I get to start and few that I get to finish. And so although it's not my style or my preference, I am starting things today for you, but I need to go and start some other things too. And so I need to excuse myself as soon as I finish this. I really wish I could stay because this is a fascinating subject that I really look forward to hearing about, and I'll have to find some other way to catch up and learn the message from today. So with that aside, let me tell you a little bit about our speaker today. Some of you already know him. The presentation is entitled Exploration of Pluto by New Horizons, and our speaker today is Dr. Alan Stern, who is the principal investigator of this mission. But he's also a familiar face to many of us at NASA because from 2007 to 2008, he was the associate administrator at NASA headquarters in the Science Mission Directorate. And under that tenure, he is known for having sponsored a number of very successful accomplishments and missions, one of which was our very own Laddie during that time that he was associate administrator. So we're deeply appreciative of the support for that mission, and some others that took place during that tenure featured the first woman principal investigator for a number of missions. One of them was the Discovery class mission for Grail. Another one was an Explorer class mission for New Star, and finally Living with a Star, the Star Geospace Mission of Opportunity, the Barrel mission. So that was really a pioneering set of historic events too that took place while he was with NASA. He's been involved with 27 suborbital, orbital, and planetary space missions, including 8 for which he was the principal investigator on the mission. It all started, I might point out, as a summer intern at Johnson Space Center. And the year that took place has been omitted for the sake of the innocent, but needless to say, it's a very strong endorsement of student internships and the value that they create for individuals in their careers. Dr. Stern completed 2 master's degrees in aerospace engineering and atmospheric sciences, and bachelor's degrees in physics and astronomy from the University of Texas. Dr. Stern earned his PhD in 1989 in astrophysics and planetary science from University of Colorado. He has published over 250 technical papers and 40 popular articles and has received numerous awards, including the American Astronomical Society 2016 Carl Sagan Award, and very recently he paid us a visit just a month ago to receive the NASA Distinguished Public Service Medal. In 2007 and 2016, Dr. Stern was listed among Time Magazine's 100 most influential people in the world. So I hope you are equally influenced by everything that he has to say today, and please help me in giving a warm welcome to Dr. Alan Stern.
Well, thank you for that very generous introduction. And that didn't raise the bar at all. So I want to say thank you for having me out to Ames. It's always great to come out here. I see a lot of people in the audience, but it's very hard with the lights to see who's where. One of the great things about New Horizons is it's a team. And coming out here to Ames, I want to point out for those of you that don't know it, Ames plays a big role in New Horizons. Dr. Dale Cruikshank, who I know is sitting over there, is one of our co-investigators. I know there are quite a number of collaborators on the New Horizons science team that are here today. We have other co-investigators from Ames, like Jeff Moore, who's not here today, but I was with Jeff in Arizona earlier this week. He runs our geology and geophysics imaging team. We have co-investigators at the SETI Institute and at Stanford, and so the whole Bay Area is really very well represented on New Horizons. Now, for today, I'm going to give a sort of soup to nuts talk about how we got to do this, what it was all about, and some of the discoveries that we've made, and then I'll connect it to a couple of other things at the tail end. And so let's just go ahead and get started. I'm going to do most of this with a clicker, and there you go. Meet Pluto. I suspect most of you have seen this natural color image of this distant little dwarf planet over 3 billion miles away. This is an image mosaic made by New Horizons data showing the close encounter hemisphere that we explored in detail last July. But prior to last July, this was the best image of Pluto that had ever been made. It's as good as it got for almost 85 years from the time of Pluto's discovery until we sent a spacecraft there. This image was made with the Hubble Space Telescope. I mean, you just can't do better because it's diffraction limited and above the Earth's atmosphere. And I have to tell you, embarrassingly, because I was the PI of the Hubble program that took this image, that we wrote lots of papers about that. Even though we knew that what you really need are data like this to understand a planet, right? In fact, if you take this image of the Earth, from which you can do real science if you had been doing your first flyby of the Earth, and pixelate it to the same resolution as that image of Pluto, which I had one of our New Horizons postdocs, Amanda Zangari, do, this is what you get. So what could you learn about the Earth at that resolution? It's not very much. You can't even tell that there are continents and oceans on the planet. In fact, this is the reason that we send spacecraft far away, is to get close so we can do real science. And I would like to drive that home a little further by showing this picture and asking if anyone in the first couple of rows wants to guess what we're looking at. Well, it might be Mars, but it's not, which just makes the point. Now, New Horizons was a big project. 2,500 men and women worked on it at one point or another to build it and to launch it, and then a very small team flew it across the solar system. It's the first mission in NASA's Science Mission Director New Frontiers program, which flies approximately billion-dollar class missions. Juno, which just entered orbit around Jupiter, is the second mission in that sequence, and the third one, called OSIRIS-REx, which will sample a near-Earth asteroid, is going to launch next month. And you might wonder, how did we get to do this, right? To explore the farthest worlds that humans have ever explored, to win a mission to Pluto, and then get to build it and fly it, and then have lots of fun with the data. I have to say, it took a while. I first got the bug to be a part of something like this in 1989. And NASA conducted the first real study of how to do a Pluto mission just after Voyager had flown by Neptune, finishing its exploration of the giant planets. That was called Pluto 350, because that spacecraft was going to weigh 350 kilograms. But that project never got legs. It was canceled in favor of the idea of something called Pluto Mariner Mark II, which was the idea of taking the Cassini line, Cassini is a Saturn orbiter, and flying more of them, one of them the size of a houseboat, to Pluto. And then that turned out to be too expensive for what the budget could afford. So we went from houseboats to hamsters, and the next iteration was called Pluto Fast Flyby, and it was going to weigh 35 kilos, including fuel, 1/10 Pluto 350. That didn't turn out to work at all. By the time it got a good hard look, the spacecraft kept growing and growing in mass and growing in cost. And so it got canceled, and they rebooted as Pluto Express, and I won't go through all the steps, but you see it there listed in time. New Horizons was the sixth iteration, the sixth attempt to get a spacecraft all the way out to the Pluto system. And I'm saying this primarily for the students in the audience, the interns, because one of the things that it takes in space flight, and if you talk to people in other projects, even Earth orbital projects, human space flight as well as robotic, and it's true in research too, it takes persistence. You've got to really want it. The scientific community stuck with this and kept going back to the agency and the advisory committees, and every time a Pluto mission fell apart for some reason, sometimes cost, sometimes technical, sometimes the management team wasn't right, whatever, the community picked itself up off the floor and said, let's start again. And not just 2 or 3 times, half a dozen different times. Now, to get the funding to do something like this is a significant activity in and of itself. And ultimately, in the United States, things like this have to rise through an independent review process called a decadal survey. In the case of Pluto and flying a mission to the Pluto system, we were making the case all through the 90s to advisory committees that we knew many interesting things about Pluto and that it promised to get a lot of bang scientifically for the bucks that were going to be involved. At the top is an infrared reflectance spectrum of the surface of Pluto, actually made in the 1990s. Dale Cruikshank may have actually been the observer. He's saying yes. So Dale, this is Dale's spectrum. And you can see that there are quite a number of molecules whose absorption features are seen there. The interesting thing is all 3 of the primary constituents that you see, the methane bands, the molecular nitrogen bands, and the carbon monoxide, are all molecules that are capable of being mobile on Pluto's surface at the relevant surface temperatures way out there, 35 or 40 Kelvin. And so those molecules all play analogous roles because they can go from solid state to vapor phase and back, and therefore transport around the surface that water plays on the Earth, or that CO2, carbon dioxide, and water play on Mars. So this promised very interesting surface-atmosphere interactions and very complex interaction, we thought, between the geology and volatile transport. These 3 molecules being called volatile because they can transport around. We also knew that Pluto had an atmosphere, and in the lower left is a trace of an occultation, an event in which a star was observed in the late 1980s by the Kuiper Airborne Observatory, the precursor to SOFIA that Ames runs, to disappear behind Pluto's limb. And because the starlight gradually dimmed over a period of tens of seconds instead of just winking out, that team could determine that Pluto has an atmosphere that was causing a refractive effect. Many other things were learned back in that era that also promised it would be interesting. One is that Pluto's big satellite, Charon, was not only discovered, but we got the first good estimates of its size and its mass, and it turns out to be a double system. The satellite is half as big as the planet. And we learned from knowing the sizes of the 2 objects and measuring the barycentric wobble due to the tug of Charon on Pluto, what their individual masses were. And from that, we could determine the density of Pluto for the first time. And it turned out that despite being way out on the edge of the solar system, and so far from the sun and covered in ice, that it's not actually an icy planet. It's actually about 70% rock on the inside, which was a big surprise in the time. So all these things and others were arguments that were being made to review panels and to advisory groups why we should send a mission to Pluto instead of all the other good things you could be doing. And you know what? That kept getting on the A list. And that's a part of the reason that we kept getting new studies each time one would fail. The case was good enough that we'd start again. Let me tell you what put it at the top of the A list. And I have to start with a diagram of the solar system as we used to know it in the 20th century. And probably most people in this room saw something like this even in grade school when you first learned a little about the planets. There you see the way that we used to think the solar system was laid out, with 4 little rocky terrestrial planets, Mercury, Venus, Earth, and Mars on the inside, the asteroid belt, and then 4 gargantuan gas giants on the outside, and in Pluto in a funny orbit and very tiny compared to any of those other 8. Kind of a misfit. But as it turns out, that was a myopic view. It was limited by our technology, our telescope technology and our detector technology. In planetary science, everything that we see is in reflection, and so the r² diminution of light with distance isn't the problem. The problem is in reflection. It's r² going out and r² coming back, and so that's r to the 4th, and so every time you try and look a little further, it's dramatically harder. And Clyde Tombaugh discovered Pluto in 1930, and people went looking for farther things in the 30s and 40s and 50s and 60s and 70s and 80s, and they didn't find a thing until in the 1990s, and we'll start this video, which should not have sound, and or very low sound. There's Pluto rolling along its orbit, and all those dots that are popping up are cohorts in that new 3rd zone of the solar system we call the Kuiper Belt today. And you'll notice all those are real objects, and some of them are pretty big. They're not just tiny little things the size of counties or New England states, but they're the size of objects like Pluto. So this was really a revolution in planetary science. The solar system didn't have 2 zones, the inner planets and the giant planets, but a 3rd zone where all the orbits are puffed up, and most of them are eccentric like Pluto's. But we didn't know about it for a very long time. So, I used to say, well, who's the misfit now? There are more dwarf planets discovered in the Kuiper Belt than the giant planets and the terrestrial planets combined. And here you can see a collection of cohorts to Pluto and Pluto itself. And you'll see that they are very heterogeneous in their appearance on this chart, but they're heterogeneous in real life. They're not only different in their colors, but the number of satellites, whether they have atmospheres or not. There are some that have much higher, much rockier densities than even Pluto, and some that are much lower. Some have volatiles on their surface, and some just have water ice, which is as good as a rock at those temperatures. And why we have this diversity is a great problem that we have not explained in planetary science. But an even bigger problem is, who knew the solar system was so good at making planets, and that most of them are nothing like the Earth or any of the 8 that we thought were the typical ones. So it was this realization, and in fact by the National Academy of Sciences, that rocketed the priority to go do a Pluto mission from just being on the A-list to being at the very top of the A-list. Because it was realized that by studying Pluto system, we weren't just going to learn about the fascinating Pluto system, but this was the first of a new class of worlds in the outer solar system that we had not touched in 40 years of space exploration. So NASA called for proposals for teams to form and write proposals to compete to fly this mission within a fixed amount of time, to fly it before the year 2020, to arrive at Pluto before 2020, and to do it on a fixed budget that was tiny compared to the budget for Voyager, about 2 dimes on the dollar. And 5 teams formed, and one of them was New Horizons. And fortunately for us, we won. It was a very tough competition. It lasted about a year with typical 2-stage, just like Discovery is going through now, and New Frontiers is about to start a new round for New Frontiers 4. We got notified that we had won in November of 2001, and the timing and geometry to get a Jupiter gravity assist to speed us meant that we only had 4 years and 2 months to pull it all together and get to the launch pad. And so I'm also saying this for the interns. This is the core team for New Horizons, representing the 2,500 people that worked on the project. This is a picture taken at our prime mission partner, the Johns Hopkins Applied Physics Lab, in one of their conference rooms. And I just want to say, we could not have pulled this off without a really spectacular team of people. When we recruited the team for New Horizons, I know at APL, because they had not done, they'd only done 1 planetary mission at that point, no outer planets missions. People were crawling all over themselves, all over each other, to get on board this mission. And so we had the pick of the litter. And we did also, I think, our science team our team at Southwest Research, where I work, people really wanted to be a part of what we used to call the first mission to the last planet. And you know, in the 60s and the 70s and the 80s, it was a primo thing to get to be aboard an early Mariner mission to Mars or Venus, or Pioneer, the first to Jupiter, or Voyager, you know, the most storied of all of the early exploration missions. And it was something like that for New Horizons. And we asked people, we said, this is going to be hard. We're going to have a lot less money and a lot less time, and we might just fail at this. So we're going to ask you to work nights and weekends for years on end. And still people crawled all over each other to get on it. And it really worked. And I will say the reasons New Horizons succeeded is in large measure because it's such a great team. And then we spent 4 years and 2 months to design, build, and test New Horizons. And we had many, many problems along the way. Technical problems, budget problems, schedule problems, problems at every level. We had the secret sauce for how to build ultra-stable oscillators for our radio science experiment that only resided in one place. And the two gentlemen who had been doing that for 20 years died together in a plane crash 1 month after we were selected. We were canceled after we were selected and had to get restarted in a new presidential administration. We had normal human errors where people dropped some hardware. We had an entire shutdown of Los Alamos National Lab that was preparing the plutonium that fueled our nuclear power generator. And they were shut down for months, and we didn't think we could get enough plutonium to fly the mission. And there were lots of other problems. But we did it. We built this little spacecraft, and it's intentionally small. If you go to the Air and Space Museum and check it out, it's in that same hall where Voyager is, and boy, is it small compared to Voyager. We wanted to build it small so that it could travel very fast by being launched on a really large launch vehicle. Here you can see, and I think this pointer will work, so excuse me for turning away, that's the high gain antenna. This is the nuclear power source that powers the spacecraft. It's filled with plutonium dioxide. This is the spacecraft bus that contains propulsion, guidance and navigation, command and data handling, solid state recorders, thermal control, all the subsystems. And on New Horizons, they're all redundant. Fortunately, we're 10 years now after launch, and we're still only using, nothing's failed. It's all in great shape. And I like this picture in part because you can actually see the structure of the spacecraft, which is made of aluminum. Not all of the multi-layer insulation has been put on it. This is down at the Cape about 2 months before launch in Florida. And you can see, because of all the people, just how small it is. It's about the size of a baby grand piano. It weighs about 1,000 pounds or 480 kilos when it's fueled. It carries 7 scientific instruments. The inset names them. So there are 8 imagers aboard, 8 monochromatic imagers. Some are very wide band, basically the entire visible. Others, individual colors, like a red channel and a near-infrared channel, and a blue channel for that matter, and narrow channels to image in like the methane band, and also panchromatic channels that we have several of. And then there are spectrometers, both an ultraviolet spectrometer to study Pluto's atmosphere and search for an atmosphere around its moon Charon, and an infrared spectrometer to do the same kind of thing that Dale Cruikshank's chart was showing you, except instead of showing you an average for the entire surface, to be able to look in each and every place. In fact, the infrared spectrometer that we flew can take 64,000 locations simultaneously and deliver a spectrum in a matter of seconds. So amazing technology. There are also 2 plasma instruments on board to study the interaction of the solar wind and charged particles with Pluto's environment. A dust counter built by students, the first ever student-built instrument to fly on a planetary mission. Radio science, total of 7 different instruments with 8 different sensors, and together they weigh they weigh less than the camera on Cassini, and they only draw 30 watts combined, all 7. And that miniaturization was where we put a lot of the advanced technology development money for this mission, because prior to New Horizons, typical instruments weighed more than our whole payload of 7. This is a picture of the spacecraft in the launch shroud, and I'm in front of it. And this is the day that we fueled the RTG, the radioactive thermoelectric generator, and New Horizons came alive and our mission control started operating it even though it hadn't been launched. This is Friday the 13th in January of 2006, our lucky day. And I show this picture because when we fueled the RTG, of course it was radioactive at that point, and so they didn't want people around it until they closed the hatch that has a radiation shield. But they let 5 of us get our picture taken, and I asked to be last as PI, because I knew this would be the last picture ever taken of New Horizons. So I'm very proud of that picture and all the work that those 2,500 people put in to build this launch vehicle and this spacecraft and to get it tested basically in record time. And then we put it up on top of an enormous Atlas V launch vehicle built by Lockheed Martin and Boeing, which have since amalgamated in the launch vehicle business to be ULA, the United Launch Alliance. And NASA did what I never could do as a kid building Estes model rockets, and they got the decal on without a single crease. And then we launched it 6 days after we fueled it on the 19th of January 2006. Now, this is a very big launch vehicle, and I imagine some people, particularly some of the interns, have never been to a launch of a big launch vehicle. This one's over 220 feet tall. And I'll tell you, as a kid that used to buy Estes model rockets on a very limited allowance and a lot of car washes, it was so much fun to pick this guy out because I had the budget to trick it out with everything Lockheed Martin could offer, the most number of solid rocket boosters, the lightest weight nose cone, everything. And then we put this very tiny spacecraft on top. This launch vehicle was built to launch very large satellites the size of a school bus. But we put something on, larger than this podium, but only a few times larger. So we basically took the biggest launch vehicle we could buy, tricked it out, and launched it essentially empty. And the end result is that it lifted off the pad at 2 Gs of acceleration. It was so light. And was in Earth orbit 8 minutes later. And I never get tired of watching this launch, so you get to watch it. And this does have sound, so I'll mostly be quiet. I think I have to start it. And it only runs about 90 seconds.
Go Atlas.
Watch how fast this baby goes up.
This is
when
Atlas
it crosses
launch control at
the cloud
10,
deck, it's at 10,000 feet.
9,
only
8,
seconds after launch.
7, 6, 5, 4, 3, 2, 1. We have ignition and liftoff of NASA's New Horizons spacecraft on a decade-long voyage to visit the planet Pluto and then beyond. That's 15 seconds. Everything continues to look good as the Atlas V vehicle climbs away from Florida's east coast. The 5 solid rocket strap-on boosters are burning just fine, sending the New Horizons spacecraft on its way to the very edge of our solar system.
Coming up is the staging where the solid rocket motors separate because they're finished. They've spent all their fuel. You'll see them come off in 2 groups. First, I think 3 come off and then 2. Or it's 2 and then 3. There you go. And there it went off into orbit. We flew halfway around the Earth that afternoon to the injection point to accelerate out towards Jupiter for that gravity assist. It reignited the Centaur upper stage, burned it to depletion. Then the solid rocket motor built by Boeing fired. New Horizons is so light that at the end of that solid rocket motor firing, the spacecraft was pulling 14 Gs. And it became the fastest spacecraft ever launched. As a comparison point, New Horizons, Apollo missions used to launch at 25,000 miles an hour and took 3 days to reach the moon. New Horizons did it in 9 hours. That's right. And we flew across the solar system in record time, too. First to Jupiter in just over a year. I recognize Galileo Jupiter orbit took 6 years to get to Jupiter. Cassini, which was flying by, took 4. 13 months we were at Jupiter for that gravity assist. And then we flew all the way across the solar system. So I'm going to skip about 9 years between 2006 and 2015, except to say that during the flight to Jupiter, We had to get the spacecraft, all the prime and redundant systems checked out, all 7 instruments up and running, calibrated for the Jupiter flyby, and navigate to the very precise window in space where a Jupiter flyby will take you to Pluto and not somewhere else. We thought that was kind of important. And we did that right. The gravity assist was successful. This was kind of a stress test for our spacecraft. We planned hundreds of scientific observations. We were not the first mission to Jupiter. In fact, we were the 8th. Juno is now the 9th. But we produced a lot of science as a result. And we got a great shakedown cruise, thank you, because this was the only thing we passed along the way. And then we flew it across the rest of the solar system. And I hope I can start this video. There you go. From Jupiter across the orbit of Saturn in 2008, Uranus in 2011. Now, Saturn, Uranus, and Neptune were nowhere near where we crossed their orbits, by the way. And then off towards Pluto. And there the video ends, and it looks like we missed, but we didn't. And then we started a 2-year flight operation that's still continuing, which is our flyby. Started in January of last year. Thank you on the timing. And began with approach phase imaging, looking for hazards, navigating to the aim point between Pluto and its big moon Charon. Then the flyby itself, all the close approach stuff was in July. And then we started downlinking the data. And for comparison, we took 250 times as much data as Voyager did on its Neptune flyby. And we took 5,000 times as much data as the first mission to Mars. So that, combined with the low cost of New Horizons, meant that it would take a long time to get the data back. And here we are in August of 2016, 13 months after the flyby, we're still sending data back. And it will continue until about November 1st or late October. There's a lot of data up there still that we haven't seen. And we share the Deep Space Network, and so it takes a while. So now let me tell you about flyby results, and I'd just like to start by showing our project manager, Glenn Fountain, who led this project from the time of our critical design review until just earlier this year when he retired. And there's our mission control and one of our flight controllers. And here's the Pluto system as viewed by New Horizons on approach. And you can see Pluto, and that's the encounter hemisphere with the heart on it. It's about roughly the width of the United States, somewhat smaller, but that's the scale there. Next to the upper left is the big moon called Charon, which looks distinctly different from Pluto, and is about 17,000 kilometers away. And then 2 of the 4 small satellites are shown there. Those are the 2 larger ones called Nix and Hydra. Here are the 4 small satellites in more detail as seen by New Horizons in a montage as if they were above the limb of the big one, Charon, so you can get a relative size. And these are, the 4 of them, Styx, Nix, Kerberos, and Hydra, are shown in order of their distance outward. And you'll notice there's a little one and a big one, and a little one and a big one. And we're not sure if that's telling us something important about how the satellite system formed, or if it's just a coincidence, because there's only 4. There aren't that many ways to arrange them. But it is very interesting. These are 4 space rocks, the smallest of which is about 15 kilometers, and the largest of which 70 kilometers. So these are like asteroids that we've had flyby missions of, whereas Pluto and Charon are literally small planets. They have been rounded by self-gravity. They're in hydrostatic equilibrium. This is the binary. This is the pair that all 4 of the small ones orbit, shown in exaggerated color, where we, in the computer, stretch the color so you can see the color boundaries much more easily. But we stretch the color for the whole image, and so you can see that Pluto is much more colorful and diverse than its big satellite Charon. And it's also brighter. It's much more reflective. Some parts of its surface are almost 100% reflective. Other parts are as dark as dirt, literally, only perhaps 10% reflective. But the satellite, Charon, is uniformly much darker and has much less color diversity. Here's Charon in more detail. It looks like a typical icy satellite of one of the giant planets. It's about 1,400 kilometers in diameter. I think you'll notice immediately that it's got a lot of craters on its surface. And you'll notice in a minute when I show you Pluto, a very different situation. But this is because Charon's internal engine ran out a long time ago, and Charon has no sensible atmosphere. In fact, we looked very hard and set very strong upper limits. And the combination of those two things means that this is an ancient surface that's been collecting craters as they've rained down over 4 billion years. In fact, we age date it to that age. You can see across the equator that big canyon system. It's an extensional tectonic belt that's probably the largest one in the entire solar system. And it's probably caused by the fact that early in Sharon's history, when it was much warmer, the water ice on the inside was liquid, and then it froze and expanded, and that expansion cracked the surface across this vast scale. And you'll also notice that the North Pole, which is at the top, has that funny red stain of a color. Anybody that works in 245 or in Dale Cruikshank's group knows about tholins. Those are the radiation processing products of things like methane and nitrogen and carbon monoxide that we see on Pluto's surface, but we don't have any evidence of on Charon. So we hypothesize that Pluto's escaping atmosphere, some fraction of it lands on Charon because Charon's in the way of some of the atmosphere as it's trying to leave. And at the poles where it's coldest, it can condense out, and then over time, ultraviolet and charged particle radiation can turn those raw materials like nitrogen and carbon monoxide and methane into these tholins that when Dale produces them in the lab on a cold finger are just this color and have just the same kind of spectrum. And there's now a paper in press at Nature on this topic where you can read a lot more about it. That paper's by Will Grundy, who runs our surface composition team. We learned a lot of other things about Charon, but I'm running out of time, so I'll take questions about Charon if you like, and I'll just move on. Pluto is the star of the show, and I noticed that this view graph doesn't work. You're just seeing blankness. So I'll go right to this one that shows not only very rugged terrain on the surface that told us immediately that all those materials we'd seen from Earth, which are structurally weak, like nitrogen, molecular nitrogen, had to only be a veneer on the surface, that there's something stronger, namely water ice that makes up the crust of Pluto. And you can also see, you don't have to have a spectrum to see it, you can see Pluto's atmosphere in this image, which was made 15 minutes after closest approach, because you can see the haze layers that are very good at scattering the sunlight forward to the spacecraft that was on the far side of Pluto. We study Pluto's atmosphere in detail. We use our ultraviolet spectrometer called ALICE to do that, to study its air glow, to get its the vertical structure, temperature and pressure structure of the upper atmosphere through a solar occultation. We determine the pressure at the surface with the REX radioscience instrument. It's about 11 microbars. We found that the atmospheric escape rate was much lower than all the Earth-based studies that indicate. And those mountains that we saw on the surface that you saw 2 images back not only are prevalent across the surface, and they're very high. They're typically 3 to 5 kilometers. So they're taller than the Alps. They're like the tallest of the Rockies. They're also, in some cases, covered with snows of methane. That bright material, by the way, this image is about the scale of western Colorado. And so those mountain ranges are like ranges in the Rockies. And as I say, they're about the same altitudes. And they have snow caps, which I just think is just a fantastic sci-fi thought, because we don't find snow caps very many places in the solar system. And to find snow caps in the Kuiper Belt on the first time you visit the Kuiper Belt, I just think is one of the coolest things that we found. But scientifically, even cooler is that big heart on the surface turns out to be an enormous glacier with 1 million square kilometers. And this is the northwest quadrant of that glacier, which we informally call Sputnik Planum, after Sputnik, the first satellite. That's where we are on the disk in that green box. These are mountain ranges that ring Sputnik Planum. And here's where the ice field abuts it. And if you look carefully, you'll find out the same thing that our geologists found, that there are flow patterns in the ice. Wherever there are obstacles like those islands that are sticking up, this glacier is alive. And I don't mean that it's biologically alive, it's geologically alive. And when we look at it carefully to count craters, we can't find any, which tells us that this glacier is very young. The best estimate of its age is that it's less than 10 million years old, which is a lot older than anything in San Francisco, but super young compared to the age of Pluto. 4.5 billion years old. And we can age date some units on the surface of Pluto that are 4.5 billion years old. We also see other evidence of dynamics on the surface. Here in the northeast part of Sputnik, we see a giant ice fall, that maybe an avalanche that came out of these mountains thousands of feet above the plane and came out and pooled right there over a scale about the size of the San Francisco Bay. So this is a lot of ice moving. And very recently, again, no craters on it. So in Pluto's recent past, there's been a lot of geologic activity. In fact, we believe, and this made the cover of Nature, Bill McKinnon on our science team published this paper. That ice is convecting. There's a heat source below it. We're not sure what that heat source is. We're surprised that after 4.5 billion years, a small planet can generate that kind of heat. And we see lots of other weirdness. We call this bladed terrain. Some people call it snakeskin terrain. These are aligned ridges of methane ice 1,000 feet high individually, stretching over hundreds of kilometers in a terrain type that's never been seen anywhere else in the solar system. Elsewhere on Pluto, we see what look like giant shield volcanoes, like on Mars, 100 kilometers or more across. Nothing like this has been seen in the deep outer solar system except on Pluto. It's much more Earth-like or Mars-like in this respect and several others. We see places like, if you look carefully up here, where we see what the geologists call dendritic networks that could be the result of fluid flow in the past on the surface. We see things that look for all the world like frozen lakes on the surface of Pluto. That can't happen now. There's not enough atmospheric pressure to make liquid nitrogen or anything else possible on the surface. We're below the triple point. You needed pressures that were orders of magnitude higher in the ancient past, but this seems to be evidence for a very different Pluto with a much thicker atmosphere long ago. I'm going to skip some evidence I'm out of time, I don't want to talk about, but I will say there are lots more data sets. These are composition maps in 3 different molecular bands. These are plots that show us that we can age date individual surface units, and that we find not only are some surface units ancient, billions of years old, 4 billion years old, and Sputnik is very young, about 10 million years, but we found units that are in between. So Pluto's been active throughout its history, we've learned. We've learned from counting craters on Pluto's surface a lot about the impactor population in the Kuiper Belt at size scales that you can't probe with any telescope, even any telescope that's planned, like the 30-meter telescope that will become operational in the 20s, or James Webb, could not see down to these sizes. But by counting the craters and measuring their sizes, we can determine how big the impactors are, and we've ruled out some models of the Kuiper Belt. My next to last little bit on Pluto is to show you this image sequence, which is a mosaic created from New Horizons imagery in that extended color. And this is as if, how do I start this? No. There we go. Yeah, great. Because this is a lot of fun. We're going to zoom down over the surface, use our highest resolution imagery. You'll see the rectangle of the region. Starting out at the limb, we'll come down onto Sputnik. This is about 70 meters per pixel, starting out at the limb. You'll see lots of craters. You can see structure inside the surface, stratigraphy. You can see some linear features that are start appearing right about now on the surface that might be the result of atmospheric phenomena interacting with the surface. And then this hilly region that transforms into bigger and bigger mountain blocks, individually 30 to 50 kilometers across and in excess of 10,000 feet high. And then off onto the shoreline of Sputnik Planum, you can see convection cells in the glacier. If you find any craters, let me know. Lots of other interesting detail. And all of this is available on the web, and a lot of it's already in the planetary data system, so you can have at it yourself. This is my absolutely favorite picture of the entire flyby as a guy that worked on this for 26 years, because it's an image of sunlight filtering through Pluto's atmosphere and can only be taken from the far side of Pluto. So it's my "we did it" image. It's in actual color, not exaggerated color. The skies of Pluto are in fact blue to your eye if you were to see them from this vantage point. And then I'm going to close by saying just a couple things to put this in perspective. These are 2 New York Times covers. The one on the left is July the 16th, 2015. The one on the right is July the 16th, 1965, 50 years before to the very day. It's the first flyby of Pluto on the left and the first flyby of Mars. 50 years. There are probably people working at Ames that were young engineers or scientists then. And they, in the space of just that amount of time, NASA was first to every planet in the solar system. It's pretty impressive. And that's it. You can only be first once. And across the entirety of the solar system, it's our space agency that did all of it, from Mercury to Pluto. Now, many other space agencies have done many other spectacular things, and we love having partners in planetary exploration. But it's also important that over all those congresses and administrations, this space agency was supported and had the technical talent to go and do all those things. And we were really proud as the New Horizons team to run that anchor leg in the relay of the 9 planets known at the beginning of the space age. For all of us that worked on New Horizons, this was super emotional. And we don't usually talk about things that way, but when having worked on this a long time, we got to Pluto. This is a live picture taken by a professional photographer who we asked to stand in the room when the first high-resolution image was shown to the science team, just after it got to the ground. It's just amazing what this meant to all the people that worked on it. But it also meant a lot to people around the country and even around the world. Thousands of people came to where our mission control is in Maryland. There they are on flyby day, part of them. But you know, I'm sure you saw a lot of this because you're all in the space program. People got really wrapped up in what we did. And we weren't sure they would because nothing like it had happened in a generation since Voyager. But we got the Google Doodle. I mean, how do you beat that? We're on the covers, NASA counted 458 newspapers, front page, on the same day. Our website had over 1 billion visitors in a day, 10 times the previous record for NASA, and countless magazine covers, and it was just crazy what the public response is. And continues to this day. We've given hundreds of public talks between our science team members and our engineering team, and people are still asking. We get about 10 requests for public talks every week, and radio interviews and TV shows, and I'll go back to my favorite image of Pluto to end this. People love exploration. I don't think they can get enough of it. I think it's just wonderful. And I think, and for this agency that is at the earliest stages of beginning a journey to Mars, if one little robot the size of a baby grand can generate this much interest by going to a frozen remote planet 3 billion miles away, can you imagine the inspiration it will be to send our fellows, men and women, to Mars? Thank you very much.
Excellent. Great. Perfect. Thank you, Brian.
Or is it too late?
Yeah, no, we're fine. So we have time for a few questions. Please raise your hand. Wait for the mic. There's only one runner. It's one question only. Stand up. Thank you.
Hi, great talk. I was wondering what got the fire burning in your belly for doing this, because you've been on this for 26, 27 years. So I mean, like, that takes a lot of perseverance and passion to do this. So what was it that kind of like set you on this course to do this?
Well, 3 things I would say. One is I was really interested in the science. I did my master's thesis with some computer models of Pluto's atmosphere and just was all wrapped up in the mystery of the place. Part of it was a chance to be on the last train to Clarksville, I was too young to get on Voyager. And Mariner missions were, I was sucking my thumb. This was a chance to be a part of, as I said, what we used to call the first mission to the last planet. And then part of it, honestly, and a few people in this room know me, part of it was that after we got started, we got canceled. And I was kind of upset about that. And then we got canceled a second and a third time, and the more we got canceled, the more I wanted to make it happen. And so that's true of a lot of us that were on it. And I think that combination of things, it didn't seem like 26 years doing it, at least not most days. But it does take a little persistence. Thank you for that question. Who's next? I think the runner is in charge of who's next.
Hi, very interesting talk. Thank you very much. 2 weeks before the New Horizons flyby, the Sophia telescope observed the atmosphere of Pluto from New Zealand. Could you comment on how significant these observations were for you?
Absolutely. That was, I believe, on the 29th of June. There was a very bright stellar occultation kind of event that actually discovered Pluto's atmosphere. And Sophia accepted a peer-reviewed proposal by others, not directly the New Horizons team, to go fly way down the southern hemisphere and observe that. And that was very important. And in fact, I wrote a letter of support for that proposal because for 85 years, Pluto was an astronomer's planet. We were observing it from Sophia and Kuiper Airborne Observatory and the Hubble and telescopes on the Earth and other NASA observatories. And then for about a month, it was the New Horizons data collect. And then we're back to the astronomical era again. So having a tie point for the atmosphere where we saw it from the Earth at the resolution and spectral resolution that we can get from the Earth, at the very time a spacecraft was doing the in situ and the high resolution work, grounds us for all the decades going forward with James Webb and Sophia and large ground-based telescopes for studying its atmosphere. And at the same time, we put an entire campaign together so there were also ground-based observations of the surface and of the satellites and other things, because we knew we wanted to anchor everything in time at the time New Horizons was going by as a fiducial, as a reference point. So I consider it really important. Who's next?
You had a couple pictures of convection cells in the glacier. It's kind of hard for me to imagine convection in a solid, and I was surprised not to see more like crumbling at the edges of the cells. Can you comment how that works?
As much as I can, because I'm not a geologist, so I'm going to play one on TV for a minute, because this isn't going to be on YouTube. The convection happens when you have a buoyancy-driven flow. And depending upon the gravity and the viscosity of the ice and the temperature differential from the surface down to the bottom of the glacier, you'll have different characteristics of the convection. You could do the same experiment if you put a little oil in a pan of water and heat it up. And different oils with different viscosities or different amounts of heat or different sized pans will produce different convection cell patterns. And Bill McKinnon, who led that paper, actually took the patterns that are seen there, the scales of the individual cells, for example, and by knowing something about the height of the way the surface is bowed, and by knowing some other things, he could model the temperature difference that must take place from the bottom to the top of the glacier, derive how strong the energy source takes to generate that heat differential, and as he showed in that paper in Nature, and others have as well. In fact, in Nature, another paper has shown that convection is a very good explanation. But then that begs the question, what's driving that energy source? And there are a bunch of ideas out there. And I don't know if any of them are right or one of them is right. My favorite is that we also have pretty good evidence that Pluto has an internal ocean, like Enceladus and like Europa and other worlds, and that ocean is slowly freezing over time, which reduces the latent heat resultant from that freezing. And that acts like a battery that's still powering Pluto and is driving the convection. Now that's my favorite idea. We'll see which one over time pans out to be correct, whether it's that one or another. Okay, next question if there's time.
It's so fascinating that you've got now an N equal 2 sample of the Kuiper belt. And Charon and Pluto are so different in some ways. I mean, obviously the Tholen issue and the internal heating potential and stuff. Do you have any sense about whether or not we're going to see more Charons or more Pluto-like things as we eventually begin to interrogate the Kuiper belt in greater numbers?
Well, that's a great question. And I would say we have an N equals 6 because we have the 4 little satellites. And we are going on in an extended mission now to both have another flyby of a small KBO in 2019, and we'll study a lot of them at relatively close range. But as far as planet-sized KBOs, New Horizons can't reach any of them. They're too few and far between. And as I said at the outset, we already know from ground-based that they have different colors, different surface compositions, different densities. We see this heterogeneous population. Some of them do look like Charon. They're water ice covered, and they have similar densities to Charon. Some of them look a lot more like Pluto, and some just look completely different. And so, as PI of New Horizons, I'd be the first to get in line to say we ought to fly more flyby missions out in the Kuiper Belt because we've got a lot to learn, not just about the ones that look like Pluto and Charon, but also the ones that are different or more exotic. So I think we have our work cut out for us in the Kuiper Belt. Fortunately, the 21st century is young. Yeah.
So with that, please join me in thanking Dr. Alan Stern for an excellent talk. Thank you again.